Hi everyone. Thanks for responding to me in the chat there. The YouTube panel, something's changed on YouTube's, and the panel that says how many viewers there are doesn't seem to always work. The numbers bounce around, and I get concerned that I'm just talking to empty air. But there do seem to be some people here. Anyhow, today we're just going to do a couple of problems on. One on center of mass, which is pretty easy, but I wanted to give you an example of that for the assignment that's actually due today. And we're also going to do one on rotational kinematics, which is the new material, and it's the video that you should have watched earlier this week. Next week will be rotational dynamics, and that'll be it. Okay, so before I start, though, I just wanted to say a few words about how I'm going to change the format next semester. Or I should say, I'm thinking of changing the format a little bit next semester. And I'll put this in an email next week so that everyone sees it. But I'm just kind of curious what people think. It seems that the live streams, they're a bit sporadic in their attendance. And that's okay. I mean, I understand the whole point of doing the live streams is that you could, if you want, be here and then ask questions as I'm doing it, or you could watch them later because they're recorded and then they go up on the YouTube channel. But it seems that maybe a better approach might be to just do 3 hours of pre-recorded lectures, and of course you still have to be able to ask me questions, and have a 3 hours actually in classroom optional, and it'll be something like maybe a Tuesday. I'm thinking of a Tuesday evening from 6 to 9. This would be actually at the college, and we'd have to follow the rules of wearing masks and so on, but we would actually be physically together. Okay, so the change would be to instead of having like about an hour and a half of pre-recorded lecture and then about an hour and a half of live streaming, or I guess 2 hours of pre-recorded and 1 hour of live streaming, we would actually have 3 hours of just pre-recorded, and then 3 hours, up to 3 hours of physically being together in a classroom. Okay, optional. Okay, would not be necessary. And this, I think, would give maximum flexibility because if you don't want to, if you don't feel like you have to ask questions, you should just watch the videos, do the assignments, and do the tests, and that's fine. But if you do want to ask questions, you wouldn't have this forum, which is a bit rarefied. Here I am talking to you. I'm trying to emulate as a live lecture as best possible, but we would actually be physically together in a classroom, and you'd be able to ask me questions there. But if you wanted to ask me questions via email or via Google Hangouts, I'd still provide that, although I wouldn't be able to do it every night of the week. But maybe 3 nights out of the week, you'd be able to ask me questions like that. So it'd be a slight change of format that way. And I've mentioned it to some people. They seem to like it. They say, yeah, that sounds like it's good because they want to be, we want to get past this abnormal situation. I was really hoping that I'd be back in the classroom, that we would all be back in the classroom. The material that I'm presenting is no different, but it does make a difference, okay, to actually like physically see people, to get to know them. I just know your names very vaguely. It just doesn't feel like a very healthy environment for learning, and give you the maximum flexibility so you could watch the videos at any time you like, but at the same time give you the option of being physically together and me solving problems for you. What we would do is if you come with problems, I'd help you with your problems or questions, or if you'd come without any problems, that's fine. I would just, like I'm doing right now, I would just do problems on a whiteboard, okay? And give you examples of problems that I would ask on a test or assignments. And that would be one change. The other change is more of a logistics change. I have to follow the syllabus, and in the syllabus says basically the way I wrote it was, you're expected to do the test on the test dates, and the assignments due on the dates that the assignments are due, and I didn't allow for any possibility of uh, late assignments or late tests, with the exception of emergencies. And people make decisions based on the syllabus, and so I can't change the rules halfway through the semester. And some people they're just a little bit they're not reading those emails that I send out every morning, and they become somewhat disconnected from the course. And some people miss the test, and they didn't see it till much later, and that's no good. Okay, so what I'm thinking of doing is just relaxing that a little bit, but not too much. I mean, that's the reason I send out those emails every morning, and they're repetitive on purpose, because I know that people just sometimes don't read them, and then you don't read them for a week or maybe even 2 weeks, then you can get into the trouble that there's a test um, that we're going to have. And I do even say what the test dates are. But what I think I'll do as a logistics change is that if you know do the test a day late, it's like 10% off, and 2 days late, it's 20% off, and so on for no more than 5 days or maybe 4 days, because eventually I have to make the answers available. Okay, and if I make them available, well, if I make them available to one person, and then anyone can have them, and so I can't extend it forever, but maybe I can make a little bit of a window in there, okay, and relax it a little bit that way. This way, if something happened, you could do it later, but then there's a penalty. None of this is neither of those 2 points are set in stone. I'm just putting it out there for people, and like I said, I'll email it, and then you can give me feedback. And if you have other ideas, I'd be more than happy to consider them. I mean, teaching online, it's different. This is the first time I've ever done it like a total class this way. And the first times you do it, you always encounter things, and you go, I think I could do it better next time. So that's why I would like to implement that for the next semester. But I'm happy to hear what you guys say, and I talk with my other colleagues about what they're doing. So we'll see. Okay, anyhow, that's enough for now, and let me know what you think. Okay, so let's start with our first question. The first question is a center of mass problem. And unlike the center of mass problems that you saw on the assignment, if you've done the assignment, I didn't even give you a picture here. Okay, there I gave you a picture. It was kind of an ASCII picture. It was still something, but these problems are easy enough that if I just give you the data like this, you don't even need a picture. When we're done with the problem, we'll look at a diagram to get some intuition. But they are really straight. These are really straightforward problems. So just to show you how they're done, let's do one together. Okay, this is a 2D problem. Okay, so find the center of mass of the following system of masses at the given locations. Okay, so you have a 3 kilogram mass, and it's at location x is equal to negative 1.3 meters and y is equal to 1.4 meters. Okay, then you have a 4 kilogram mass at some location, a 5 kilogram mass at another location, and finally a 1 kilogram mass. Okay, and so where is the center of mass for this? The center of mass is a point in the object which is kind of like the middle of the masses, but it's actually a weighted average. Okay, and it is a vector because in 2D it's a point in a 2D plane, and to identify a point in a 2D plane you need a vector. Okay, so there's going to be an x component and a y component. Okay, and so the two are calculated independently of one another, and so here's the formula for the x component right here. Okay, and what is it? Well, there's a numerator and a denominator. There's the numerator, and basically you just add up mx for all of the masses. So here we have 4 masses, and here the first one has m1 times x1 plus m2 times x2 plus m3 times x3 plus these ellipses mean plus all the rest of the masses. Well, we only have one more, so it would be plus m4 x4, but if we add a fifth one, it'd be plus m5 x5, then m6 x6, and so on. Okay, so there's the numerator, and then divided by the denominator, and that's just the sum of the masses. And it's a weighted average if you've done statistics, because the bigger a mass is, the more it tends to draw the center of mass towards it. And we'll see that when I draw the diagram. Okay, and the rest of it is like just literally plugging in. So as long as you're careful, there should be no problem. So m1, there's 3, x1, that's negative 1.3. Okay, and then m4, right? Sorry, m2 is 4, and x2 is 1.95 right there. Okay, and so on. So this here is basically this column here multiplied by that column right there. There's no y because in in any of these problems, when you're working in Cartesian, there's a complete decoupling of the x and y information, and so to calculate the x component of the x component of the center of mass, you just use the x information. Okay, so there's the numerator, and then the denominator is just the sum of the masses. And you work that out, and you get 0.742 meters. Okay, so there's the x component. The y component, it's the same formula, but you replace your x values with your y values. So you have y1 instead of x1, y2 instead of x2, and so on. Okay, and the next line is it's not a typo. I actually have x there. All I'm trying to show with this is that it's the exact same formula here. In fact, I just cut and paste that, and all you do is just remove the x values there. And what do? You replace them with the y values right there, there, and there, and you get the value for the y component of the center of mass. Okay, and so now you're using this column right here. All right, and that gives you a y component of negative 0.135 meters. Okay, so there's your center of mass. There's the x value of the center of mass, and there's the y value of the center of mass. Okay, that would be it. And then you multiple choice. You would just I see which one matches up. Let's take a look at a diagram so that we could see how this weighted average is working. Okay, so let's take a look at this diagram right here. What I have here is the four masses at the x and y components as specified. Okay, and the center of mass, we found the x component to be at 0.742. So if I just draw this in blue here, let me get my blue pen up. Okay, so x is this is x equals 1, the first tick right there. So 0.742, that's somewhere around there like that. And we can just draw some dashed line up like this and dashed line there down like that. Okay, and the x, that's the x value. So the center of mass has to be somewhere along that line. The y value turned out to be negative 1.35. So that's, negative 1.35 is somewhere around there like that. And then draw a dashed line there like that. And where the two cross right there, that's where your center of mass is. Okay, and so if you take a look at this, you go, it's kind of like close to the 4 and the 5 kilogram, and that's right. These two masses are the bigger mass. Okay, and then there's the 1 kilogram. It contributes a little bit. Okay, and then there's the 3 kilogram way off over there. But you can see that these masses here tend to pull the center of mass closer to it. If I were to increase that 5 to say to, like, I don't know, 10 or even more 20, then this center of mass would progressively move closer and closer and closer to that, like that. Okay, because the bigger that mass is, the more it tends to draw it towards it. Okay, the other masses have a bit of an influence. Okay, so they pull it a little bit their way, but this mass here would pull it much more. Okay, so yeah, it kind of makes sense that the center of mass is right there. The other thing is, if you draw kind of a perimeter here like this, if you draw like a line between there and there and there, and you make this quadrilateral like that, the center of mass has to be in the middle of that, or not in the middle, but within that quadrilateral. Okay, you couldn't have a center of mass out here, for instance, and you go, well, why not? Well, because these masses, each one of these masses, they're trying to pull the center of mass towards it, and so there would have to be a mass out here that would tend to pull the center of mass towards it, and there isn't one. Okay, so there's no way that the center of mass could ever be outside of that quadrilateral. It'll be somewhere inside of there. Okay, so it doesn't tell you where it's going to be, but it's at least a little bit of a check, and it gives you a little bit of intuition into what that center of mass is. Okay. So there's the first question, and really they can't get much deeper than that. I mean, I'd have to give you information about the masses. I'd have to give you information about the location. I mean, the only thing I could make maybe more complicated is give you polar, and then you'd have to convert to Cartesian, and maybe back again. But that would be just like kind of a gratuitous complication. It doesn't really get at the notion of a center of mass. Okay, and there it is. And so, what is the center of mass? Okay, so that's how you solve these problems, but like physically, how do you think of them? And so, like, if you have an object like, my remote here, okay, the center of mass is like, I don't know, somewhere in the middle here like that. We'll see next semester when we do statics. That's actually our first topic next semester. That if I put my finger directly below the center of mass, whoops. I can't quite get it, but that the object balances. If my finger is directly below the center of mass, like maybe there, not too bad. Okay, there we go. All right, so my finger is not at the center of mass; it's below it. But if my finger is below the center of mass, the pivot point's below the center of mass, then it would balance. Also, if I throw this into the air, it would spin. Okay, the center of mass, if you follow that, that follows the parabolic trajectory that we talked about earlier in the course, but not the entire object. The entire object would rotate around an axis through the center of mass. Okay, so so the center of mass is kind of important, and in fact, I mentioned in the pre-recorded lecture that the motion kind of decouples. It decouples, and there's so when you describe the motion of an extended object, you could describe the motion of the center of mass, and that's everything that we've done up to this point in the course. Like when we talked about parabolic motion of projectiles and things like that, we weren't talking about the entire object because that doesn't describe the rotation of the object. That just describes the center of mass. Or when we did, like masses on inclined planes, I said, put all the forces in the middle. Really, we were putting all the forces at the center of mass. Okay, we weren't thinking about the extended nature of the object. But now we've kind of generalized that and we say, well, let's talk about the extended nature of the object. And in that case, the center of mass becomes critical. Okay, and this is how you calculate it. Okay, let me take a quick peek in the chat here, see if there's any questions about how this is done. I'm not seeing any questions. Let's move on. Okay, it'll be a short course, short class. There's no reason to extend it and do more than we have to. Okay, so the second problem, I actually got looked up a centrifuge on Amazon.com. So a centrifuge, maybe you've used one in chemistry or in biology. They spin. You put these test tubes in it, and they spin, and as the test tubes spin, they produce what you might call artificial gravity, and it separates out the fluids. Okay, so if you got blood in there, all the heavy stuff in the blood, like the cells, they'll go to the bottom end, and the plasma, the fluidy part, will rise to the top. Or if you've got milk in there, it'll separate into the various layers of milk, with the heavier stuff, the denser stuff, going to the bottom and the less dense going to the top. Okay, so centrifuges are used to separate colloidal solutions that way. Okay, so I looked this up, and all the numbers are real except for this 45 seconds. Okay, I just didn't know how long it takes to spin up, and I couldn't see that in the specifications. But we have a centrifuge, and it starts from rest. Okay, and it spins up to 5,000 RPM in 45 seconds. Okay, so you can imagine you put the test tubes in there, you close it, and then you turn it on, and it starts spinning slower, and then faster, 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 and then after 45 seconds, it's spun up to 5,000 RPM. Okay, and RPM stands for revolutions per minute. All right, the bottom of the test tubes, okay, because the test tubes are sitting in there, and then the opening is closer to the axis, to the axle around which it spins, and the bottom of the test tubes are the furthest. Okay, so the bottom of the test tube experiences an acceleration of 3074 g. Again, that's actually one of the specifications. Okay, that's a lot of acceleration, by the way. We'll see how much that is in a minute. So 3074 g, what does that mean? G here means acceleration due to gravity. Okay, so technically 9.8, but we'll round it off to 10 meters per second squared. Okay, so that's how much acceleration, an object at the bottom of those test tubes, that's how much it experiences, how much acceleration it experiences once this thing is spun up to 5,000 RPM. Okay, and then I just say assume constant acceleration, I guess for the first 45 seconds. All right. So that's our situation, and then I ask some questions. The first question is, what's the angular acceleration? Okay, so what's angular acceleration mean? It means not how fast it's spinning, but how fast it's spinning up, the rate at which it spins up. So if it's spinning at 5,000 RPMs and it just stays at 5,000 RPMs, there's no angular acceleration. But if it starts from 0 and then it goes to 100, 200, 300, all the way up to 5,000, it's speeding up. Its angular velocity is increasing, and in that case, there's an angular acceleration. Okay, and this is spinning up, and so I asked for my first question, what is the angular acceleration? All right. Second question is, how many times does it actually turn during the first 45 seconds? Okay, so it starts at rest, and it's going to make 1 turn, 2 turns, 3 turns. Now, the time it takes to make a turn decreases, but you could still count how many times it's turned in that first 45 seconds, and I want to know that number. How many times is the centrifuge turned during the first 45 seconds? Okay, as it spins up. The third question is, what's the centripetal acceleration at maximum speed? Okay, so once it's spun up, what's an object at the bottom of that test tube? What acceleration is it experiencing? Okay, and how far is the bottom of the test tube from the axis? Okay, so when something spins, it spins around an axis, like a door. When a door turns, not that it's really spinning, but it's still turning. There's a spin there, so I should say any kind of rotation. Any kind of rotation occurs around an axis. For a door, those are the hinges. Okay, there's an axis that passes through the 2 or 3 hinges that holds the door in place. Okay, with this object here, if I grab it at the end here like this, my 2 fingers are holding it in place, and then I turn it like that. Okay, and the axis around which it's turning is between my 2 fingers. Okay, so there's an axis, and the bottom of the test tubes are some distance from that axis, some radius from that axis. Find that distance. Okay, and I actually don't know the real number, because that wasn't part of the specified answer, but the answer that I got calculating it was pretty reasonable, and we'll see that in a second. Okay, and then finally, how fast is the point at the bottom of the test tube moving? Okay, I'm actually asking for the linear velocity or the tangential velocity. Okay, not how fast is it spinning, but like if I were to measure, like, how fast is it moving? How many meters per second is this thing moving at? Okay, as it moves. I know it's moving along a curve, but still, you could ask how fast is it moving along that curve. Okay, so there are the questions. Let's start. So to answer the angular acceleration question, it's probably best to start with the equations for angular kinematics. Okay, now angular kinematics, assuming constant angular acceleration, constant alpha. Okay, so there's the first equation. There it is. Okay, and this is slightly different than the way I usually write it, but it's probably a better way to think about it. And the way I usually write this equation would be like this. It'd be like theta here is equal to that plus theta naught, like that. Okay. And what is this? Well, it says, look, if you start at some angle theta naught, some orientation theta naught measured by an angle, and you start with some initial angular velocity omega naught, and you have some angular acceleration alpha, and you wait a time t, then you're now at a new angle theta. So you start at this angle theta naught, and you wind up at this new angle theta, and this is the equation that gives it to you. Well, our initial angle, and that's not so interesting. Okay, that's kind of like tantamount to choosing an origin. So it's more interesting to look at the change in the angle. Okay, so if I subtract theta naught from both sides, I subtract theta naught from this side, then I lose my theta naught over there, and I get this equation. Okay, and then the next thing is like, that's kind of ugly there to say theta minus theta naught. That's just your change in angle, like I wrote there. Okay, and so this I'm just going to replace with theta naught, and when I do, I get this one. Okay, so this is not different. I don't remember exactly how I did it in the pre-recorded lectures, but that's no different than the other way that I just wrote it. Okay, it's just, this is a little bit better to think about, because you're not thinking so much about like what orientation you're in, what angle. It's like, what angle did you turn through? And that equation will give it to you. Okay, so here's the second equation, and that is like, if you start off with some angular velocity omega naught, and you got an angular acceleration alpha, and you wait some time t, then you wind up at some other angular velocity omega. Okay, and then the third one is just these other two with the time eliminated between them. Okay, so let's go through it and see what we know. Let's read the problem again. A centrifuge starts from rest. Okay, so starting from rest means you're not turning. Not turning means your angular velocity is 0. Your initial angular velocity is 0. Symbolically, that is omega naught equals 0 radians. Okay? The second thing is, how fast does it spin up to? Well, I say that it spins up to 5,000 RPM. Okay? So our omega, our final velocity, is 5,000 RPM. That's not an MKS. RPM is revolutions per minute, okay? And revolution is just turn. It's like, how many turns does this thing do in a minute? It does 5,000 complete turns every minute, which is pretty fast, okay, if you think about it. So in 60 seconds, this thing is turned 5,000 times, okay? But we need it in radians per second, okay? So, because that's, all my equations only work if you're in radians and in seconds, okay? So, we need to convert the time. So minutes here is in the denominator, so we put it in the numerator in our conversion fraction. And 1 minute is equal to 60 seconds. Okay, so 1 minute divided by 60 seconds, that will eliminate the minutes there and give you seconds, okay? And then revolution, you want to convert from revolutions to radians, and revolutions in the numerator here, so you put it in the denominator of the conversion fraction, and 1 revolution is 2 pi radians, okay? And so that converts that to radians per second. Excuse me. So there you go. Now, just to know that you're in the right ballpark, because you might make a mistake here or something, if you've got it in revolutions per minute, roughly dividing by 10 will give it to you in radians per second. Not exactly, but just roughly. Okay, so you expect the number to decrease by a factor of roughly 10. And if you take a look here, you went from 5,000 to 523.6. Okay, so, I mean, like if you flip one of these fractions around, you'll get a totally wrong answer. So, just as a check, yeah, this number should be roughly 1/10 of that number. Okay, great. We've got the final velocity in radians per second. How long does it take to spin up? Well, 45 seconds, okay, and that's all you know. Okay, so there you've got those. You look back at our equations here, and you go, which one can I use? And you can't use number 1, and you can't use number 3, because you don't know alpha. That's what you're trying to find, and you don't know theta. You just don't know it, and so the only one you can use is number 2. And so you start from equation number 2 there, like that. Substituting in omega is that, and so there it is. Alpha is what you're solving for. T is 45. Omega naught is 0. And ta-da, you get an alpha of 11.6 radians per second squared. Okay, so there's our first question. All right, let me see if there's anything in the chat there. Okay, you guys are doing fine so far. Okay, so how many times does the centrifuge turn during the startup time of 45 seconds? In other words, how many times does it turn during that first 45 seconds? Okay, now this question is a little bit, students can get a little bit confused over it, and that's because I'm asking how many times does it turn. And now you look at these equations up here and you go, well, which one is turning? I mean, like what variable corresponds to turn? And it's actually the angle. It's actually this angle here. And you go, well, I don't understand that. How is an angle turning? Okay, usually when you say angle, you think of like a wedge, and you think about that angle in there. But a turn is an angle, or an angle is a turn. Okay, an angle could be like a fraction of a turn. So, if you say something like a quarter of a turn is 90 degrees. Half a turn is 180 degrees. Okay, a complete turn is 360 degrees. Okay, now I'm saying that in degrees because most people think of degrees better than radians. Okay, but if I said an eighth of a turn is 45 degrees. Okay, so you can see that a turn and an angle really are the same thing. You say, well, what if I do 2 turns? Well, then that's going to be 2 times 365. What if I do 3 turns? Well, then that's 3 times 365. Well, what if I do 3.5 turns? Well, then that's 3 times 365 plus 180 for that half turn. And so you can see that the number of turns and the angle really are the same thing. Okay, so the language will sometimes trick you. You'll get caught up in the language, and you'll say, "What is he asking for? Number of turns? I don't see number of turns as any one of the variables." It is. It's the angle. Okay, so you could use either equation 1 or equation 3 here. Either one has delta theta in it, and that's what we're solving for. Okay, I chose number 1. I don't know, just because I guess delta theta is already isolated. All right, so there it is. And then substituting in, it's pretty trivial. We know alpha now. Now we know alpha, 11.6, so we substitute in for that. 45 seconds squared. There's no initial velocity, so that's 0. So that works out to 11,745 radians. Okay, now that is the answer, and my tests are multiple choice. So if you see that my answers are in radians, then you say, well, I got to match 11,745 radians. Okay, and hopefully one of the answers is that number. Okay, but suppose you look at my answers, and my answers are in turns. And after all, I did ask the question, how many turns? How many times does the centrifuge turn? Okay, so I'm kind of suggesting that I want the answer in turns. And you go, but I don't have the answer in turns. I have it in radians. Well, what do? Convert back. Okay, so here it is. Radians is in the numerator, so you want radians in the denominator, and then to form the fraction. Remember, this fraction has to equal 1. one revolution is 2 pi radians, and so 1 revolution divided by 2 pi radians, that's equal to 1, and you can always multiply by 1. So this whole thing is like multiplying by 1, but it's a cleverly crafted one such that the radians will disappear, will cancel out, and it'll be replaced by revolutions, and you get that it's 1869.3 revolutions. Okay, so that's how many times this thing would turn in that first 45 seconds, which if you think about it is quite a lot, quite a lot. Okay, I mean, this thing is really spinning pretty fast. All right, okay, let's move on to the next question. The next one is, what is the centripetal acceleration at maximum speed? So if we go back to the problem, the way I worded it, you say, well, I mean, usually when students see a question like that, they'll go, well, what equation do I need? Okay, well, the answer is stated in the problem, the number is stated in the problem, but in a slightly cryptic fashion. So think about what I'm saying. Okay, so when something is spinning, think of uniform circular motion. I know this isn't quite uniform circular motion, but it is after it finally spins up to 5,000. It starts off slow, 100, then 200, 300, 400, 500 RPM. It spins up to 5,000 RPM, and then it doesn't spin any faster. So it reaches the maximum, and then it spins at 5,000 RPM. Well, that 5,000 RPM, once you're up there at that rate, you don't spin any faster, and that means that you're at constant rate, a constant angular velocity. That is uniform circular motion. In uniform circular motion, there is an acceleration because even though the thing is moving at the same speed, it doesn't speed up or slow down, it has to turn. And any change in the velocity, whether in the magnitude or in the direction, is an acceleration. So there's going to be a turn. This thing's turning all the time. And as it turns, there's an acceleration towards the center. And that acceleration towards the center is what's causing the acceleration in those test tubes, which is causing the separation. And I tell you what that is, at least at the bottom of the test tube. The bottom of the test tube experiences an acceleration of 3,074 g. Okay? And so down here, when we solve this problem, what's the centripetal acceleration? That is this 3,074 g. Okay, so there's g. But you need it in MKS, so what you do is you just take out g and multiply 3,074 multiplied by g, and you get that the centripetal acceleration is 30,740 meters per second squared, which is huge. Okay, basically that is 3,000, like anything at the bottom of that test tube would weigh 3,000 times more than it weighs ordinarily. Okay, humans can barely handle like at 7G, like from 7 to 9G we faint. Okay, if you're in a fighter jet, maybe you can experience 7G for a few seconds, but if it continues too long, you'll actually faint. 3G's on a really wild carnival ride or something like that, but you wouldn't enjoy it for very long. This is 3,000 G's. Okay, so the acceleration that's experienced by the whatever bacteria, cells, or whatever are in that test tube, is going to be extreme. They'll get crushed. Okay, they're not going to be those poor bacteria are not going to be very happy campers in there. Okay, so there it is. There's the centripetal acceleration, and we give that the symbol AC. Okay, now actually when you have uniform circular motion, you only have centripetal acceleration. But when you actually have an angular acceleration, there's also a tangential. Not only is the velocity turning, but it's also speeding up. And so the turning gives rise to the centripetal acceleration. The speeding up gives rise to the tangential. But the centripetal acceleration is much, much bigger than the tangential. We'll see that in the last problem here. So in the last problem, it says, second to last problem. How far is the bottom of the test tube from the axis? Okay, you say, well, what's this got to do with acceleration? Well, there are two accelerations, like I just mentioned. There's the centripetal acceleration, and then there's the tangential. You say, well, which one do we want? That's the one that's going to be much bigger. We'll see that when I get R in just a second. That's the one you want because that's the one that's responsible for really causing that separation. The other one is small. Okay, so if we use this formula right here, There it is. And we isolate R because that's what we're trying to solve. AC, well, we just calculated that. That's that 30,740 meters per second squared. Okay, so there's your centripetal acceleration divided by the angular velocity squared. Okay, we got that angular velocity. That's when we converted the 5,000 RPM to radians per seconds. There it is. Okay, and if you work that out, that turns out to be 0.11213 meters. Okay, and if you convert it to centimeters, that's 11.2 centimeters. Okay, and that makes sense, doesn't it? Okay, 11.2 centimeters. I mean, if you gotten an answer which was like a meter, that doesn't make sense. You know, centrifuges are about, you know, this big. And the test tube's inside, you know, there's the axis right there. The bottom of the test tube, it's about 10 centimeters from the axis, and we got 11.2. Now, I couldn't find that number in the specifications, but that makes sense. I mean, I've used them. Maybe some of you have used them, and so 11.2 centimeters, yeah, makes total sense. Okay, and that uh, um, uh, that angular velocity right there at that radius right there gives you that 30,740 meters per second squared. Okay, now while the centrifuge is spinning up, there's also this tangential acceleration. Let's see how big that is. It's the formula for it is different. So for the centripetal, it's r omega squared. For the tangential, it's just r times omega. Well, r we now know is 0.11213, okay, in meters. The acceleration we found above, angular acceleration we found above, is 11.6 radians per second squared. And if you work that out, that turns out to be 1.3 meters per second squared. Well, compare that 1.3 to that 30,000. I mean, I think you'll agree that the centripetal totally swamps out the tangential. The tangential is absolutely negligible. It's there. If it weren't there, it would spin faster and faster and faster. So you need a little bit of a tangential acceleration to speed it up as it spins. But as it starts to spin, okay, faster and faster and faster, it's that centripetal acceleration that's really big and really doing all the work in a centrifuge of separating out the colloidal solution. Okay, so there we go. That's that question. And then the final question is, how fast is that point at the bottom of the test tube moving? Okay, and that's given by this formula here. Okay, the tangential velocity, that is, you know, imagine that you're like a speck running along with the bottom of the test tube as it goes around. I mean, you're moving at some velocity. Okay, how fast are you moving? Even though you're turning, you've got some velocity, some linear velocity. And you say, how fast is that? And that tangential velocity is given by r times omega. And so r we have from the previous question, omega we have from above, and that turns out to be 58.7 meters per second. Okay, now how fast is that? Like, how fast is 60 meters per second? That's pretty fast. It turns out to be 211 kilometers per hour. And, you know, over 200 kilometers per hour, that's probably going to be like 130 miles an hour. So this is moving very fast. And so as a safety feature, these centrifuges, they have a lid. You got to close the lid because you can imagine if it's spinning this fast, you put your finger in there, you're going to get really hurt. Okay, these things are spinning extremely fast. Okay, so there it is. That answers the last question. Okay, let me see if there's anything in the chat there. Otherwise, we're done. I mean, it was just kind of short. I wanted to make sure that we covered, that I showed you some problems, how to solve problems, covering the material that we've done. Okay, I'm not seeing any questions. Let me just end by telling you what we're going to do next week. It's the last topic in the course, and it's rotational dynamics. And basically, we're going to do the rotational equivalent of Newton's law, tau equals I alpha, the rotational equivalent of energy, and the rotational equivalent of momentum. Okay, and so basically it's a similar formulas to what we had before, but just like you see here, where like theta replaces x, omega replaces v, and alpha replaces a. Okay, for the position, velocity, and acceleration. Okay, you have the same kind of thing happening there, but in the rotational world. So there's a rotational equivalent of mass called the the moment of inertia. Okay, and we'll work with that next week. And that's it for the topics in the course. The week after that, that's Thanksgiving, and there's just 2 days there. So I don't know what we'll do. I might just say, you know what, take those times off. The last week, um, or maybe make it optional. Okay. The last week we'll review for the test, and then the final test. Don't quote me on this, but I think the last day of classes is December 4th, and so that'll be the day that we'll have the final test, and then that's it for the course. Okay. So there we go. If there's no questions, let me just look again. Looks like everyone's okay. Let me just say here, if everyone is okay, we're done, and I'll end the stream. All right, good. All right, wait a few seconds just to make sure the 30-second delay is, everyone got me. All right, everyone got what I said. Okay, bye-bye.